The program introduces random variables and the statistical tools used to describe uncertainty in financial markets. A random variable represents numerical outcomes associated with uncertain events, such as asset returns, interest rates, or portfolio losses. The topic explains that discrete random variables are commonly summarized using a probability mass function, PMF, which assigns probabilities to each possible outcome. The PMF provides a complete description of the likelihood distribution for discrete outcomes and ensures that the sum of all probabilities equals 1. This framework enables risk managers to organize uncertain outcomes systematically and evaluate the probability of specific events occurring within financial and operational environments. The program then explains cumulative distribution functions, CDFs, which measure the probability that a random variable will take on a value less than or equal to a specified amount. Unlike a PMF, which focuses on individual probabilities, the CDF accumulates probabilities across outcomes and provides a broader perspective on distribution behavior. The program emphasizes the relationship between PMFs and CDFs by demonstrating how cumulative probabilities are derived from individual probabilities. CDFs are particularly important in finance because they support the estimation of loss probabilities, confidence intervals, and risk thresholds such as value at risk, VAR. Analysts frequently use cumulative distributions to evaluate downside exposure and probability-based investment outcomes. Another major topic is expected value, also known as the mathematical expectation of a random variable. Expected value represents the weighted average of all possible outcomes, where each outcome is multiplied by its probability of occurrence. The concept provides a measure of the long-run average outcome if a process were repeated many times. In finance, expected value is critical for estimating anticipated returns, forecasting cash flows, and assessing investment opportunities. The program illustrates how expected values are calculated for discrete probability distributions and emphasizes their role in portfolio management and risk assessment. Financial institutions rely heavily on expected value analysis to evaluate risk-adjusted performance and strategic decisions. Topic introduces the 4 common population moments used to describe the characteristics of probability distributions: mean, variance, skewness, and kurtosis. The mean measures central tendency and represents the average expected outcome of a random variable. Variance measures dispersion by quantifying how far outcomes deviate from the mean, while standard deviation provides the square root of variance in more interpretable units. These measures are fundamental to modern risk management because they capture both expected returns and uncertainty. Higher variance indicates greater volatility and risk exposure, which is particularly relevant in portfolio optimization, derivatives pricing, and financial forecasting models used by risk professionals. The program also emphasizes skewness and kurtosis because financial return distributions often deviate from the assumptions of normality. Skewness measures the asymmetry of a distribution around its mean. Positive skewness indicates a longer right tail with potential for large gains, while negative skewness reflects a longer left tail associated with substantial losses. Kurtosis measures the thickness of distribution tails relative to the normal distribution. High kurtosis implies fat tails and a greater likelihood of extreme outcomes. These concepts are extremely important in risk management because traditional models based solely on variance may underestimate the probability of rare but severe financial events such as market crashes or systemic crises. Topic transitions from discrete random variables to continuous random variables through the introduction of probability density functions, PDFs. A PDF describes the relative likelihood of continuous outcomes occurring within a given interval. Unlike discrete variables, continuous variables have infinitely many possible outcomes, so the probability of observing any single exact value is 0. Instead, probabilities are measured across intervals using areas under the density curve. The program explains that PDFs are widely used in financial modeling because many economic variables, including asset returns and interest rates, are better represented as continuous distributions. Understanding PDFs enables analysts to estimate probabilities, model uncertainty, and evaluate continuous risk exposures effectively. The topic further explores quantiles and quantile-based estimators, which divide distributions into specified probability segments. A quantile identifies the value below which a given percentage of observations falls. The median, for example, represents the 50th percentile of a distribution. Quantiles are highly important in finance because they are widely used in risk metrics such as value at risk, stress testing, and scenario analysis. The program also discusses the interquartile range, which measures the spread of the middle 50% of outcomes and provides a robust indicator of variability. Quantile-based methods are particularly useful when distributions are skewed or contain extreme outliers that may distort traditional statistical measures. Finally, Topic explains linear transformations of random variables and their effects on statistical properties. A linear transformation takes the form y equals a plus bx, where constants adjust the location and scale of the original variable. The program demonstrates that the mean and variance change predictably under such transformations, while skewness and kurtosis remain largely unaffected except for directional changes in skewness when scaling factors are negative. These principles are highly relevant in financial engineering and portfolio management because analysts frequently transform variables when standardizing returns, adjusting for inflation, or converting risk measures across different scales. Understanding transformations allows risk managers to interpret and manipulate financial data consistently within quantitative models.